Let's go through a few conceptual questions. These conceptual questions will be related to what we've been talking about, waves and wave speed. So as usual, answer the question on your own. Even if you're not certain, just choose the answer you think is correct and then watch the solution. And please reach out to me, my students, if you have questions about it. So here is our first question. So this correct answer is A here. We're talking about a wave pulse on a string. So for a string, the speed of the wave depends upon the force of tension and the linear mass density. We want this wave to travel twice as fast on the same string. So all we're doing is changing and adjusting tension, and we need to know what to do to tension to come up with twice the speed. We can get 2V by multiplying the force of tension by 4. If we factored out the square root of 4, that would leave us still with our beginning square root of tension over mu. But the square root of 4, of course, is 2. And so we would end up with this 2 times the force of tension over mu. If you want, you can also think of that as I want 2 times this original velocity. And then to bring the 2 under the radical, the square root, we have to square it, and we can see that we end up with the 4 in there in terms of the force of tension. So by increasing the tension by a factor of 4, the speed of the wave will be double. And this is a wave pulse, but the idea is still the same because the speed, the wave itself travels at the same speed, whether it's a continuous wave or a wave pulse. Let's look at a second question. What do you think here? So the correct answer here is A. So light is our electromagnetic wave. We know that the speed of light in a medium with index of refraction n is equal to the speed of light in a vacuum, 3 times 10 to the 8th, divided by n, the index of refraction. And so if we're talking about light entering a material that has a higher index of refraction, n's bigger, then v gets smaller. So it slows down as it enters a new medium. Well, a new medium with a higher index of refraction specifically. All right, one more conceptual question. What do you think here? The correct answer here is B. So if I have this string, it's got to be attached to something at this end. It's saying that you're wiggling one end. That essentially means you're shaking one end either up and down or side to side. But by doing that, you're causing waves to travel down the string. So the speed of the wave is down the string. It would also reflect some of it and come back. It says as we wiggle more rapidly. So we're increasing the frequency. So how fast we're shaking this string up and down or side to side. but we're not affecting the tension in any significant way. So the speed of the wave on the string is the force of tension over the linear mass density. We're not changing this tension. We're not changing the linear mass density because it's the same string. So we are not changing the speed of the wave at all. But again, we have this relationship that the speed of a wave is equal to wavelength times frequency. And the gut instinct typically is, well, if I make frequency bigger, we expect the left side to get bigger too. And so we really want to say that the wave's going to travel faster. But that's not the case. The speed is staying the same because we haven't changed the tension, we haven't changed strings, so we have the same linear mass density. The result, if the frequency gets bigger, this wavelength will get smaller. So the peaks we would see on the string would be closer together. That wavelength would be measured smaller. So again, this equation is very simple, but it is at this point one of the most easily confusing equations, just because of how we're used to looking at equations. So keep in mind the speed of a wave depends entirely on what the wave is traveling through. So what kind of wave is it? What is it traveling through? If we're not changing the medium, what the wave is traveling through, then we're not going to be changing anything about the wave speed, I should say.